Chromatography, GCSE, iGCSE and General Chemistry. It's very important when using Chemistry Explained not to be passive. So write notes, complete tasks as you move through the lesson. Control the pace. Skip ahead if you wish. Replay slides or run the whole lesson at a quicker pace. Very importantly, when prompted, pause the lesson, think the problem through, taking your time and complete the task. When you're ready, continue the lesson, checking your work and then going on to the next slide. So chromatography will cover methods and simple analysis of chromatograms, locating agents, careful which exam board you are following, and then retention factor values. Paper chromatography and thin layer chromatography separates soluble substances, that is, solutes, and can identify them. The setup is a chromatography tank or beaker with a chromatography paper, a lid to prevent evaporation of the solvent. A pencil line is drawn on the paper strip at about 1 centimeter from the end. And then that paper, chromatography paper or TLC plate, is placed in the solvent. The solvent may be referred to as the mobile phase, in that it is going to rise up through the chromatography paper, which may be referred to as the stationary phase or containing the stationary phase. Over time, the solvent rises up and forms a solvent front. So to produce a chromatogram, a concentrated spot of solution is spotted on the pencil line by repeatedly spotting on the same spot and labeled. So here is our concentrated spot on the pencil line. The chromatography paper is then placed in the tank with a suitable solvent and lid. Two things about the solvent: the mixture must be soluble in the solvent, or chromatography as a process will not work. Secondly, the level of the solvent must be below the pencil line. The solvent rises through the chromatography paper, of course, and it takes different solutes with it at different speeds. What does this chromatogram tell us about the original black solution? Pause, think it through, come back when you're ready. Okay, so to continue, it's a mixture of 3 different solutes. The original black mixture has separated into 3 different solutes by traveling at different speeds up through the chromatography paper or thin layer plate. Quick thought: what would the chromatogram for a pure substance look like? Think it through or draw it out. Come back when you're ready. So to reveal, of course, our original spot on the pencil line above the level of the solvent will rise with the solvent, but as there's only a pure substance, there is only one spot produced. So this would be the chromatogram for a pure substance. To identify components of a mixture, pure samples are often used. Solutes are spotted on the pencil baseline and labelled, but we know the identity of reference material 1, it's pure reference material 1, and we know the identity of pure reference material 2. So these are pure samples whose identity is known. We then spot two unknown solutes. We don't know what A and B is. We know what reference 1 is and reference 2 is. If we allow the chromatogram to develop, we will see something like this. Reference material 1 will rise. It's a pure substance, so it'll be 1 spot. Reference material 2 will produce 1 spot. What can we say about mixture A and what can we say about mixture B? Pause, think out an analysis, think about how you would word it carefully, come back to check on mine. Okay, so mixture A contains reference material 1 and reference material 2. So reference material 1 travels a certain distance. Well, we can see that one of the spots in A has travelled the same distance, so we conclude it is the same. So reference material 1 is present in mixture A. We also see that reference material 2 is present in mixture A. So mixture A is a mixture or contains reference material 1 and 2. If you haven't already done so, can you analyse mixture B? Come back when you're ready. Okay, so to discuss, B contains R1, it's at the same level as reference material 1, does not contain reference material 2, it contains a second material, a second solute, but we don't know what it is. So B, its R is a mixture of R1 and something else, which we don't know the mixture of, identity of, but we do know that B is a mixture of 2 solutes. So here is a problem for you to attempt. Here is the initial chromatogram, and here is the developed chromatogram. What can you say about the purple, the blue, and the red, shall we say, inks? Pause. Carefully think about what can be said. As much detail as possible. Come back to check against my analysis. Okay, so I'm going to resume. The first thing we can say is that the red and the blue are pure substances. They're only forming 1 spot. We can say that purple is a mixture of red and blue. Locating agents. So interpreting chromatograms so far depends on the solutes having colour. But what if no coloured solutes emerge? You produce a concentrated spot on the pencil line. You have solvent below the level of the pencil line. You've got a tank and lid. The solvent rises through the chromatography paper or TLC plate, and yet no spots emerge. Well, in some cases, you can spray with a locating agent. So you soak the chromatography paper or plate with the locating agent, leave it for some time. Some locating agents or some spots develop more quickly than others. Leave it for the required time and then you will see that spots will develop, which can then be interpreted in the usual way. Retention factors. retention factor RF values. Solutes can be identified by comparing the distance the solute travels to the distance traveled by the solvent in the chromatogram. This is known as the retention factor. If we measure the distance from the baseline to the center of the solute spot, let's call that distance A. So from the baseline to the center of the solute spot, and then measure the distance from the baseline to the solvent front, so from the baseline to the solvent front, and we divide the distance of baseline to solute by baseline to solvent front, we achieve a number, a retention factor value. If we refer to a database, the identity of that solute can be achieved or obtained. However, it depends on the conditions of your or my chromatogram being the same as the conditions employed by those who made the database. So what things do you think would need to be kept the same or controlled? Pause, think about it, come back to check on my ideas. Okay, so we're interested in the distance traveled by the solute. So that's going to be affected by temperature. So we need to control the temperature, make sure it's the same as in the database. We need the same solvent, and we need the same stationary phase, be it paper or TLC plate, an exact same composition. So those things need to be controlled so that we can refer to the database value and conclude on the identity of the solute. So let's finish with a retention factor problem. Calculate the retention factor value. We have concentrated spot and a solute spot. The distance between baseline and center of solute is 4.5. The distance from baseline to solvent front is 5.5. Can you calculate the retention factor? Pause the lesson, come back when you've calculated your number. Okay, so to reveal, I'm dividing 4.5 baseline to center of the solvent by 5.5 baseline to solvent front. Comes out as 0.818. Now, RF values are always going to be less than 1. A little tip for the exam. Very common, students get this the wrong way up, but it must always be, the RF value must always be less than 1. This distance here must be less than the distance travelled by the solute. Obviously, the solute can't travel further than the solvent front, but is almost certainly going to travel a lesser distance. So RF values are always less than 1. This topic will really benefit from practice in answering questions. So go to your textbook, end of chapter, go to past paper questions. If you don't have access to past paper questions, I suggest Maths and Physics Tutor, the website. Of course, there are others that are equally as good.